So for this next section, we're going to actually talk now more about how we actually can figure out what the absolute maxes and absolute mins are going to be. We talked about in the last section, in our last class, how to find the relative maxes and relative mins, but now we're going to explore how to figure out what the absolute max and absolute min is going to be. We brought up this idea about the extreme value theorem. And remember, we can abbreviate extreme value theorem as the EVT. And again, it has to be continuous on a finite closed interval. Then remember what the EVT states. Again, the interval has to be closed. Then what the EVT says is that f will have both an absolute maximum and absolute minimum. The EVT does not apply if it's an infinite interval. So if it has an absolute extremum on the open interval, then it must occur at a critical point. So in other words, if we don't have that finite closed interval, then it's going to have to occur at a critical point for the absolute extremum, if a function has the absolute extremum. So here's how we actually go about finding what the absolute max and absolute min of a continuous function is going to be. And again, we're looking at a finite closed interval from A to B. So first of all, what we're going to do is we're going to find the critical points, just like we did in the previous section. We're going to evaluate f at all the critical points and the endpoints of A and B. The largest value in step 2 is the absolute maximum, and the smallest is the absolute minimum. So when you're looking at your closed interval and you're trying to find the absolute extrema, it can occur either at the critical points or it can occur at the end point of that closed interval. So those are the two places we have to check. Again, we're talking about when we have this closed interval. So I don't know what happened here with the black. I don't know what happened in my copier. So find the absolute maximum and absolute minimum of f of x on the closed interval and state where those values occur. So first of all, you have to find your critical points. So again, we know how to find the critical points. I have to find f prime of x, which is going to be 6x squared plus 6x minus 12. I can factor out a 6, and then I can factor this and set it equal to 0. So then my critical points are going to be at x equals -2 and x equals 1. Now, what you have to be sure of, we have to make sure that these are actually relative mins and relative maxes. Sometimes they try and trip you up. If these points are not relative mins and relative maxes, then they can't be an absolute minimum or an absolute maximum. So again, doing my number line test, if I plug -3 in here, that's a negative times a negative, which is a positive. Plug in 0, positive, negative. So you can see that I do have that sign change on the graph of my derivative, so I do know that this is going to possibly be an absolute maximum. If I plug in 2, positive, positive. So now my candidates. So now I'm checking to see what my candidates will be for my absolute maximum and absolute minimum. Concur at my critical points. So x equals -2 and 1, and you have to check your endpoints. The endpoints of my closed interval are -3 and 2. So when you're checking, when you have the closed interval and you're looking for absolute max and absolute min, you not only check your critical points, but you're going to check your endpoints. And then what I always just do is I make a t-chart. So again, my critical numbers are -3, -2, and then I have 1 and 2. Now what you're going to do, we want to find what the actual y values are on f of x. So what I want to do with each of these x values is I want to plug it back in to my original function. Because remember, these are referring back to the points on my f of x. So I want to know my highest and my lowest points. So when I plug in -3, I'm going to end up with something wrong. I'm going to check myself. Yep, it's 9. And when I plug in -2, that's going to give me -16, and then 12, and then, so that's going to give me 20. And then when I plug in 1, that's -7, and then finally when I plug in 2, that's going to give me 4. So now from this chart, what you want to do is you want to look to see what the largest number you got for the y value. So right here, I've got my largest y value. And remember from my number line test, I did indeed confirm that this was a relative maximum. So because this has the largest y value, this is going to be my absolute max. My absolute minimum will happen at the smallest y value, which is at 1, -7. So that's my absolute minimum. And I did confirm on my number line that that was indeed a relative minimum. So then my absolute max, and we talk about the absolute max, you're talking about the y value, is 20, and that's occurring at x equals -2. Or you want to write f of -2 is 20. We talk about the absolute minimum. The absolute minimum, you're referring to the y value, is -7, and it's occurring at x equals 1. Or you can write it as f of 1 is equal to -7. So when you have the closed interval, you have to check not only your critical points, but you need to check the endpoints as well. When you have the infinite interval, so let's suppose that it's not that closed interval, there's no guarantees that you're going to have an absolute minimum and or an absolute maximum. Because if you look at the graphs that can occur, here's an example where you have an absolute minimum, but there is no absolute maximum. Here's an example, you have an absolute maximum, but no absolute minimum. Or you may have neither, depending upon the behavior of the function. So when you take a look at this example here, find the absolute maximum and absolute minimum of x to the 4th plus 4x over your interval all real numbers, and state where those values occur. So the only place an absolute max and an absolute min can occur is at your critical numbers. So now think about what the graph of x to the 4th plus 4x looks like. It's an even degree polynomial function, and we know the end behavior is going to go to infinity for this particular function. So right away, I know there's going to be no absolute maximum. So the only thing I can check for is there will be an absolute minimum. So the only place that this can occur is it's going to occur at a critical point. So I have to find my f prime of x, which is going to be 4x to the 3rd plus 4, and then I'm going to set this derivative equal to 0. So 0 is equal to 4x to the 3rd plus 4. I can factor out a 4. So x will be equal to -1. So again, my only critical point is -1. You still want to find the y value, because when we talk about max and min values, it's the y value that we're referring to. So when I plug in -1, that's going to give me 1 minus 4, which is -3. So my absolute minimum is -3, and it occurs at x equals -1, or it's f of -1 is equal to -3. So any questions on finding that particular minimum? So now they want me to sketch, I don't know what this black line happened here when I made this copy this morning. Sketch the graph of a continuous function f with the stated properties on the interval -5 to 5. So f has a relative minimum at x equals -3. So I have this closed interval from -5 to 5. I have a relative minimum at x equals -3. So I'm just going to kind of put a point right there. Has a relative maximum at x equals 2. Now they're saying I have an absolute minimum at x equals 5. So I know that I'm going to have to put this point way down here. That should be my lowest point on the graph. And it has an absolute maximum at -5. This black line happened right at where it says my absolute minimum was at x equals. That black line went right through where they told me that we have an absolute minimum at x equals 5 and an absolute maximum at x equals -5. So I want this at -5 should be my highest point, at 5 should be my lowest point. I should have a relative minimum at -3 and a relative maximum at 2. And again, don't put arrows at the end because you have that closed interval. So any questions on doing the sketch? So now, moving away from absolute and relative mins and max, we haven't talked about concavity a lot. Again, and that's going to be this next section, concavity. So if you have a differentiable function on an open interval, f is said to be concave up if f prime is increasing on that interval, and f is said to be concave down on the open if f prime is decreasing on that particular interval. So again, just to make sure, I always call it concave up like a cup. I don't know if that helps you. So again, when you're concave up, this is what your graph looks like, concave down. So this is an example where your slopes are increasing. This is an example where your slopes are decreasing for their tangent line. So this is where we look at the second derivative of a particular function. If the second derivative is greater than 0 for every value of x in the open interval, then f is concave up. So remember, the first derivative we use to check for increasing and decreasing. The second derivative we check for concavity. If f double prime of x is less than 0, then it is going to be concave down in that particular interval. So here they want me to find the intervals where f of x is concave up and concave down. So I have to find the second derivative and do a number line test very similar to the way that I did for increasing and decreasing. So my first derivative is going to be 3x squared minus 6x. So my second derivative is going to be 6x minus 6. So what I'm going to then have to do is take my second derivative and set it equal to 0. So 0 is equal to 6 times x minus 1. So then I end up with x is equal to 1. So I'm going to do my number line test just for my second derivative. It's not asking me about increasing and decreasing. So I need to take a test number, plug it into my second derivative to see if my second derivative is positive or negative. So if I plug in a 0, that's going to give me negative. So what that means is the graph of f is going to have to be concave down. If I plug in a 2, notice it's positive. So that tells me for numbers greater than 1, it's going to be concave up. So since my second derivative is less than 0, I am concave down from -infinity to 1. And then I'm going, since my second derivative is greater than 0, I am concave up for my 1 to infinity. We do have a special name for x equals 1. That point where you change concavity, which is what we have here, we're going from a concave down to concave up at x equals 1. We do have a special name for that point. That's called an inflection point. So the inflection point is where your f of x changes concavity. So given the graph of f of x, we want to state the sign for f prime and f double prime. So now remember, pay attention to what function they're giving you. So they're giving me f of x. So remember, if I'm increasing, I know that f prime is positive. So notice I am increasing from A to B, so f prime has to be positive. From B to C, I'm still increasing, so I know that f prime is positive. However, from C to D, notice my graph changes to decreasing. So I know that the sign of my first derivative will have to be negative. So remember, this is where you want to look for increasing or decreasing. Again, this is given the graph of f of x. To determine the sign of the second derivative, this is where you have to look at the concavity. So the sign of the second derivative is determined by the concavity. So when you take a look at your interval from a to b, so from a to b, you can see that you are concave up. So that sign is going to be positive. However, you can tell that at x equals b, you're going to have an inflection point. Because notice your graph now changes from concave up to concave down. So since I'm concave down from b to c, I know the second derivative will be negative. I'm concave down from c to d, so the second derivative is negative. So that's how you can determine the sign of your first and second derivative. Again, the second derivative, you look at the concavity. So now if you take a look at this example, find your intervals of increasing, decreasing when we're concave up and our inflection points. This part D, I don't know what happened with this black line, is going to be where f is concave down. So first of all, remember, increasing and decreasing, you look at your first derivative. Concave up and concave down, you look at your second derivative. So first let me find my first derivative. That's going to be 12x to the third minus 12x squared. So let me first deal with where f prime is increasing and decreasing. So I'm going to factor out a 12x squared, and that's going to leave me with an x minus 1. So again, my critical points are going to be at x equals 0 and 1. So when I plug in a negative 1, that's going to be negative. So I know I'm decreasing. When I plug in a 1/2, that's going to be negative. So I'm decreasing. When I plug in a 2, that's positive. So I'll be increasing. So remember, where I'm increasing is where f prime is greater than 0. So the only place I'm increasing is going to be from 1 to infinity. So now decreasing, I can write this as one interval going from negative infinity to 1. And again, remember, this is where my f prime is less than 0. So to determine where I'm concave up, remember my second derivative has to be greater than 0. Where I'm concave down, my second derivative has to be less than 0. So I found my first derivative, so now I'm going to find my second derivative. That's going to give me 36x squared minus 24x. I can factor out a 12x. That's going to leave me with a 3x minus 2. So I have x equals 0 and x equals 2/3 as possible inflection points. So if I plug in a number less than 0, I'll plug in a negative 1. So that's going to be a negative times a negative, that's a positive. So I know I'm concave up for all numbers less than 0. Here I'm going to plug in, let's say, 1/2. That's positive. 3/2 minus 2 is negative. So that means I'm concave down. And then I plug in 1. That's positive, so I'm concave up. So then I'm going to be concave up from negative infinity to 0, and then from 2/3 to infinity. I'm going to be concave down from 0 to 2/3. Inflection points is where I'm changing concavity, so it's going to be at x equals 0 and x equals 2/3. And this is where f double prime changes signs. So any questions about checking for concavity? So now given a graph, but notice I'm giving you the graph of f prime. So when you're reading the graph of f prime, remember to find where f is increasing. This is where f prime is greater than 0. So this, remember, is where I'm going to look to see where I'm above the x-axis. And notice I'm above the x-axis from here to here. So it's going to be from negative infinity to negative 1 and 1 to infinity. Where I'm decreasing, this is where f prime is less than 0. So where it's falling below the x-axis. So that's going to be from -1 to 1. Again, you look above and below the x-axis. Now, where I'm concave up, so this is where my second derivative is going to be greater than 0. So when you're given the graph of f prime, your second derivative, you're looking at the slope of your tangent lines. So to figure out where you're concave up, you want to see where f prime is increasing. Because again, this is where I'll have all positive slopes of the tangent line. So I'm looking at the derivative of this particular graph. So my second derivative will be greater than 0 from 0 to infinity. Concave down, this is where f double prime is less than 0. Or this is where I'll look at the graph where f prime is decreasing. So you can see the slope of all my tangent lines are negative for all my x values less than or equal to 0. So that's where I'd be concave down. Notice you are changing concavity at x equals 0. So you do have an inflection point at x equals 0. The graph that's least descriptive, or that we can find the least amount of information from, is when we're given the graph of the second derivative, or f double prime. So the only thing we can tell about the graph of the second derivative is the concavity. Remember, we're talking about the graph of f. We're always referring back to whatever the original f is. So remember, to figure out if we are concave up, f double prime has to be greater than 0. So again, we can see that the graph f double prime of x is greater than 0 from here to here, and then from here to here. That's the only place where the graph of the second derivative is above the x-axis, or where it's positive. I'm just going to put a tick mark here at -2, and same thing here at 2. So I can see that I'm going to be concave up from -2 to 0, and from 2 to infinity. Remember, to be concave down, I'm looking to see where the second derivative is less than 0. So where is it going to fall below the x-axis? We can see that the only place where f double prime falls below the x-axis is in these two intervals right here. So it's concave down from -infinity to -2, and then from 0 to 2. So to way that we can identify inflection points, we need to see where f double prime of x changes sign. So when I'm reading this graph, I'm looking to see where it crosses over the x-axis. So we can see that I'm crossing the x-axis here, here, and here. So I'm changing from a negative to a positive, positive, negative, and then negative to a positive. So I have 3 inflection points. X equals -2, 0, and 2. Okay. So now to do a sketch, a possible graph with the following conditions. They're giving you f of 3 is equal to 2. This is a point. F prime of 3 is equal to 0, that means I have to have a turning point or a horizontal tangent line. So that could mean it could be a relative minimum or a relative maximum. F double prime of x is greater than 0. When x is greater than 3, that means this graph has to be concave up. The second derivative less than 0, that means I have to be concave down when I do my sketch. So what I'm going to do is I'm going to start by putting the point on the graph. And again, remember, that has to have a horizontal tangent line. So remember, at 3, I have to be concave up greater than 3. I have to be concave down less than 3. So if I kind of look right here, I can make this graph like that. Again, I'm concave down, and then I change to concave up. And again, I do have that horizontal tangent line. So when I take a look at the next one, still give me a point at 3, 2. So this tells me the second derivative is greater than 0, I'm concave up. So the limit as x approaches 3 from the right of f prime of x is negative infinity. Limit as x approaches 3 from the left of f prime. That means the slope of my tangent lines are going to be going towards negative infinity. The slope of my tangent lines are going to be going towards positive infinity. So what this means is I'm going to have a sharp point. So again, I have to be concave up for all numbers except for 3. And you can see the slope of my tangent lines on the left-hand side of 3 are positive. The slope of my tangent lines on the right are negative. So this is a graphing calculator question. So they're giving me the cosine of x plus sine x, and they want me to find where I'm increasing, decreasing, concave up, and concave down. So on my graphing calculator, make sure you're in radian mode anytime you're dealing with trig and calculus. I'm going to type in f of x under y1. Clear it out. And again, make sure you change that window from negative pi to pi. So I'm going to graph it. Now, what I really want to see is I want to see what the graph of the derivative is going to be. So what I'm going to do is I'm going to go back to my y equals. So I'm going to graph the derivative. So what I'm going to do is I'm going to tell my calculator, go under my alpha window, choose option 3, n derivative, and again I want to sketch the derivative of the function I have loaded under y1. I'm just going to put x equals x. Now what's nice is with your graphing calculators is just so I'm not looking at two graphs, I'm going to look just at the graph of the derivative. So if I arrow back up to y1, put my cursor on the equal sign and hit enter, notice that equal sign is not highlighted anymore. Only what's under y2 is. So what that means is my calculator is only going to graph what's in y2, which is my derivative. While my calculator is doing this, remember when I look at finding where f is increasing, I'm looking to see where f prime is greater than 0. Where it's decreasing, f prime is less than 0. Where it's concave up, that's where my second derivative is greater than 0, or it's where f prime is going to be increasing. Intervals where I'm concave down, it's where f double prime is less than 0, and again, this is where my f prime is decreasing. This is where my f double prime changes signs. So when I take a look at this particular one, where is f prime greater than 0? So remember, this is the graph of f prime. So we can see that f prime is above 0 from here to here, and that's it. So I need to find these two x-intercepts. So I'll go under second trace, 0. Left bound, right bound, yes. So that's at negative 2.356. So I know my interval for part A is negative 2.356, comma. I need to find my other x-intercept, which is over here. That's going to give me 0.785. So that's where I'm increasing. Decreasing, remember, for part B is where it's going to be my first derivative is less than 0. So that's going to be from negative pi to, again, the negative 2.356. And it's going to be from this x-intercept, 0.785, to pi. So next I need to find where I'm concave up. So this is where my second derivative is greater than 0, or where f prime is increasing. So I can see that f prime is increasing from here to here. So I need to find this relative maximum, which I can do on the calculator going under second calc. maximum. So it's going to be from negative pi to negative 0.785. I'm also going to be increasing, f prime is increasing from here to here. So I can go ahead and I can find the other minimum, again, because that's a relative minimum. Feels like this cursor's moving very slowly today. So that's going to be from 2.356 to pi. And then for part D, to find where it's concave down, I want to see where f prime is decreasing. F prime is decreasing from here to here. So again, I already found this point right up here. That's my negative 0.785. And I just found that point down here, which is the 2.356. So now I can take a look to find where I'm changing concavity. So again, I'm changing concavity where f prime changes from increasing to decreasing. So I know I have an inflection point at x equals 0.785, because that's where f prime changes from increasing to decreasing. And then I'm also going to have another inflection point at the x equals 2.356. So when you're reading the graph of the second derivative, we're looking to see where f double prime changes signs or where f prime changes from increasing to decreasing.